Madame, Monsieur, bienvenue à la de 2021. I'm coming to you from my backyard here in the upper Midwest. I thought I would share with you the lovely fall day since we can't all be in Paris. I am here on behalf of DDN WAM Cloud to talk to you about single stream performance in Lustre. And this is a topic I am very excited about. Just So just real quick, little disclaimer, benchmarks. Most of our benchmarks were done with a DDNA i400 on the back end, and there's our client description, kind of pretty standard stuff, just a large client. Most of these numbers are with IOR. Actually, I think all of them are with IOR. So just, like I said, disclaimer, let's get moving. So what is single stream performance? What am I here to talk about? The definition that I'm using for single stream is the IO output from a single user space process using basically your standard POSIX interfaces. How fast can DD run? Actually, DD is not that fast, but maybe IOR or something similar. And this is interesting for its own sake. There are single stream portions, single process portions of a lot of different jobs, but really it's interesting because it's the foundation of other performance behavior. The behavior of one stream defines the behavior of many, both to one file and then also both on one client and then also on multiple clients. If the behavior of an individual IO stream is nice and clean, it'll interact well with others. If it's ugly and lots of hitches in it, it won't, and you won't scale. So let's talk about how Lustre does with that. It's where we're at. This is 212, 214, and with the exception of the Rufford read, we could actually take this back to probably like 2.5, and you have about the same numbers. So these are kind of your best case single stream. Direct IO here is a little low, but you're looking at 1 to 2 gigabytes a second for buffered write. Same thing for direct IO write, direct IO read. Again, you can get a little higher on some systems. And then for buffered read, it is a fair bit faster because we have parallel read ahead now. But these numbers are fine. But they've only really increased, with the exception of parallel read ahead, with CPU speed since, I don't know, maybe 2012, which is around when I started working on Lustre. And this isn't really all that fast. GPFS is quite a bit faster, and some object stores are a lot faster than this. So why doesn't Lustre do better than that? I mean, what's the problem? There's various reasons, but we're going to talk mostly about direct IO. Buffered IO is kind of hard, but maybe we can do something good with direct IO, because of course, direct IO is simple. When you do direct IO, you require that the user give you aligned memory. It's aligned on page boundaries and the size is nice and aligned. That means you don't need to do any mem copying or allocation of pages inside the kernel. And also there's no page cache, which turns out to be really important. You don't have to insert and manage the pages, keep them kind of linked together and up to date and accessible for other processes. So it's a lot simpler than buffered IO. And even today, it's much more scalable with multiple processes. I'm not going to show any hard numbers, but a lot of you will be familiar. You can stack many direct IO processes and get very good performance, whereas with buffered IO, you start stacking processes, it depends. Mostly, you're not going to be super happy about it. One other thing that's about direct IO that is a mixed, but mostly a blessing, is that once the IO completes, it's just over. So the direct IO write call is kind of the simpler example. That data is expected to be on disk, and if there's any POSIX lawyers in the room, I know that there's some technicalities around that, and does POSIX require it to be synced? In practice, programs expect that when a direct IO call completes, their data is safe on disk. But that's costly, but it makes things really simple. So small direct IO performs badly. I guess that makes sense. It's entirely synchronous for the writes, so you've got to get the data all the way to disk. So Flash will help. But even with Flash, getting data to disk is not the fastest operation in the universe, especially not over a network, et cetera, et cetera, et cetera. And of course, because there's no cache, you can't do read ahead. So if somebody wants to read a file 4K at a time, well, they are going to read that file 4K at a time from disk. Whereas, of course, if we have buffered IO and we do read ahead, we will gladly read that file for them 64 meg at a time and then hand it to them at 4K at a time. But okay, so that's why small direct IO is slow, but there's also large direct IO. So if a user gives a large sort of buffer, either for us to read data into or a large buffer full of data to write out, why can't we do that quickly? Why is that not much faster or similar to or even slower than buffered IO? There's no cache. It should. We would think it would scale. If we assume that buffered IO is busy doing all that stuff, we don't have to do it. So why don't we scale? Turns out to have actually a kind of shockingly simple answer. Direct IO is within Lustre essentially serial. The direct, and what that means is it's serialized at the RPC level. So each individual RPC is synced before sending other RPCs. And you're kind of wondering what that's about. Well, RPC is, of course, the basic unit of sort of network IO in Lustre. So the example here, say we're using 4 meg RPCs and we send 16 megabyte of IO. Well, that will generate four megabyte RPCs. And the thing is, if you do that with direct IO today, what you do is you send 4 megabytes, you wait for it to sync to disk, and then you send another 4 megabytes. And the thing is, the user asked you to send 16. The user doesn't care about each 4. The user only cares about all 16 together. And so, but that cost, man, that's really expensive, because you got to you prep the RPC, and sync, prep the RPC, sync. And so, time is, n times number of, or number of RPCs times prep time plus sync time. And there's absolutely no parallelism at all. Everybody's weights are right. Well, you don't have to do that. I alluded to it. The user cares about their 16 megabytes of data. They don't care about each individual 4 meg. So what you do is you send all the RPCs and then you wait. It's not the easiest code change in the world. It relies on AIO and some other things. That's to be clear, it relies on AIO implementation internally. This isn't making direct IO sort of async or anything. The idea is that when the user says, I want to send 16 megabytes of IO, we send all the IO and then we wait for all of them to complete. And in practice, what that means is we have to create the RPCs and then we have to wait for the sync. But we got those syncs started a lot earlier and we overlapped them. Maybe we have multiple syncs going to the same OST, or maybe they're even going to different OSTs. But regardless, the effect is just an enormous improvement in the time. You have to create the RPCs, but then you really only have to wait for basically the last sync, essentially, because the other ones are probably complete. So, wow, that helps a lot. As you can see, with parallel direct IO, you are now looking at 4 to 5 gigabytes a second on write and read, a little bit faster on read. And that's up from 1.5 to 2, maybe you get a little over 2. And wow, right? I mean, that's great. And, and of course, here we are, and we're, 7-8 minutes into the presentation, and that's very exciting. Well, obviously, there's more to say. Can we do better? Can we do better than 4.5 gigabytes, 4.5 to 5 gigabytes a second? And the answer is very much yes. So turns out the direct IO code in Lustre is highly inefficient. And that's fine or it's been fine, because we spent all of our time waiting to sync that data, waiting to sync each RPC. And I mean, of course, especially in the era where the primary platform was spinning disk, that's really just a very long time. And even with Flash syncing data to disk is not the cheapest operation in the world. And so if the direct IO code was made more efficient in terms of generating the data on the client, kind of preparing it to go out on the wire, it didn't help much. Spent more time waiting. And the main reason for that is it's kind of does the same thing as the buffer path. Lots of careful management of all the data. We set up all these pages, we lock them, we kind of link them into various lists, we get everything ready. We don't actually put them in the cache, but we do a lot of things that would be required to get them ready to be accessible in the cache. And that's just not necessary. In the page cache, every page has its own life. Any page, anything can happen to any page at any time. Another user can come along in the middle of you doing something and say, I want to read this one page. And that has to be manageable. So each page has to have this totally separate life. That's in the buffered case, or in this page cache case. But that's not how direct IO works. Direct IO pages are not accessible to other threads. They only exist during the IO. So like you create the pages or hand them to the kernel. No one else can access that data in those specific pieces of memory while you're doing that. It's just you. And so you don't really need that locking, all that stuff I'm talking about, and this kind of careful management of, well, what's this page doing in case somebody comes to ask about it. No one can ask about it. It's not possible. That data, if somebody else wants to read or write the same region of the file, they just do it completely separately. They cannot see those pages you are accessing. They can race with you, but it's two totally separate operations. Whereas in the page cache, they actually hit the same thing. You have to hit the same pages, and so you have to handle them really carefully. We don't need to do any of that in direct IO. So what you do is you start stripping that away, removing things that are not required for direct IO. And there's a lot of just little changes, one after another, some a little bigger, just kind of one after another. And in 2.15, we've been able to cut the per page time spent in Lustre for direct IO, basically no effect for buffered IO, but being able to cut it by 70%. And before you get out your calculators and try to figure out what that means for performance, let me show you. So quick list of changes. We didn't need this slide. This is where we get to in 2.15. This is removing a bunch of the just kind of page mangling and handling and movement that is done that is not required for direct IO. We're at about 16 gigabytes a second. Actually, the best numbers we've seen are a little higher. So obviously that's pretty exciting. So this is, so your best case direct IO performance, slightly higher for read than for write, is going to be, is going to be about 16 to 18 gigabytes a second. And so I guess what more is there to do? Is there more to do? The answer is yeah, there is more to do. There is some element of diminishing returns. I mentioned that we cut out 70% of the time in page handling. And, we could, cut, there's a big chunk of what's left that can still be cut out, but that work is getting harder. It's getting more complicated. It's taking some of the deeper parts of the IO path and having to kind of split them up between buffered and direct IO, which is not, there's a lot to be said for sharing code. It's a useful, simple thing. Only one path, only one place to have bugs, only one bit of code to update, only one bit of code to change, et cetera, et cetera, et cetera. So there's kind of some diminishing returns, but what do we think? There's some existing prototype changes that aren't slated for 2.15, maybe 25 gigabytes a second, something like that. There's more after that. But I'm not going to speculate about, where the limits would be. There is still some headroom, but it's getting to be significant work to make progress on improving specifically direct IO. But so just to pause for a moment, we want to talk a little bit. Direct IO is also, one other thing about it is it's lockless. So that means there's no LDLM locking. And I don't have time in this presentation to get into all the detailed meaning of that. But what that means is, in practice, is a lot of the shared file issues, particularly around writing, just disappear. You've seen me up here in the past talking about lock ahead quite a long time ago, overstriping more recently. And those changes are aimed at solving problems where multiple clients trying to write the same file conflict on locks. Well, direct IO is lockless. That doesn't happen. So that's a pretty amazing thing. There's some pretty remarkable stuff around shared file. And I'm not showing any numbers, but if you're able to do direct IO at high speed, it has some really big benefits when you get into it. Again, so 16, 18 gigabytes a second. That's where we're at. So we do have a little more though. Not quite done. We've got buffered IO to talk about. It's stuck. It's stuck way behind. Here we are, no improvement to buffer IO. And that's too bad. And that's, it's bad. And that's a shame because, this is of course a scalability thing, but buffered IO has some real advantages and versus direct IO. And one of the big ones is it's got a significant performance advantage at smaller sizes. And this is a graph of buffered IO versus direct IO write performance with size in 214. Now, I didn't use the newer direct IO because if you notice, the numbers down at 4K were in the few hundred megabytes a second range. And if you were to take those larger numbers and use the new ones, and if the bottom of the graph is 500 megs a second and the top is 18 gigabytes a second, the bottom is unreadable. So we stuck with just this so you can see rather than showing you the new stuff. And so as you can see, buffered IO is something like 10 times as fast as direct IO at small sizes. And that's because it can do aggregation and things like that. It uses the cache to build up larger RPCs. And of course, similarly for read, it can use the cache to do this really powerful read ahead stuff. So I'll kind of repeat that. It's buffered IO is good at small sizes, but it doesn't scale. Buffered IO doesn't scale because of the cost of caching. Interestingly, by the way, the main cost in using buffer IO in the page cache is not, in fact, mem copy, and not even really page allocation. It's caching. It's setting everything up, making it all available. And the thing is, though, we still really like to use buffered IO if we could, because direct IO has to be aligned. So the user has to make sure the memory is aligned, and then they have to provide IO only in multiples of page size. Yeah, that really sucks. That's a pain for the user. And what if they want to do 8 bytes of IO or 6K of IO in the middle of some random lump of memory? Well, you can't if you want to do direct IO. You have to do something more complicated. You have to be much more involved in your file management. And that's fine for some cases and really not fine for others. So what can we do? Well, there's an insight there in the words that most of the cost is in caching for buffered IO. And note that buffered IO is responsible for aligning the memory for the user. It's not that the memory doesn't need to be aligned, it's that it happens inside the kernel. But with caching, the thing is, most data that we read from the file system or that we write to the file system is really only used once. And I don't mean that you write your data and you never read it back. But if you dump 16 megs of data to the file system all in one go, you're probably not about to read it again. Maybe you'll read it in a half hour from another client. Maybe you'll read it from their client in 2 minutes. It doesn't really matter. It's not in cache on that client, or maybe it's a checkpoint in your job and most of those are never read. And so does everything need to go in the cache? I think the answer is obviously no, right? If a lot of your data is never going to be read out of the cache, well, then you certainly don't need to put it in there. So what you can do, this has been tried at the level of a quick prototype, you can have an uncached variant of buffered IO. And this is where the data is copied to a buffer inside the kernel, but never goes in the page cache. And so this can scale similarly to direct IO because it doesn't have all the cost of carefully wrangling those data structures. One of the reasons buffered IO doesn't scale is the page cache data structures are shared. And so a bunch of threads have to access them together, which gets pretty slow after a while. And so you can switch to this for larger sizes, do standard buffered IO at smaller sizes, and at larger sizes, switch to this other thing. And basically, you create a buffer in the kernel, you copy the data into it so it's aligned, and then you do direct IO from that buffer. And this wouldn't be as fast as direct IO, but maybe 50%, maybe more, maybe as much as like 70 or 80% of the speed of direct IO. It's kind of hard to say. But as you'll remember, of course, that's a lot faster than current buffered IO. Just a lot, which was, we'll flip back a few, obviously 50% of direct IO would be a lot faster buffer IO. And this is at the larger sizes. So the idea is that we could keep the good behavior of buffered IO from the small sizes and have something more like the behavior of direct IO at these larger sizes. All right. So wrapping up, turns out if you look, direct IO is serialized at the RPC level And it turns out the code is very inefficient. And by the way, about the RPC level serialization, that was a big surprise to myself and to a number of other people, actually. I think most people working on Lustre didn't really realize that's what was going on. That I think that there was a belief, and certainly I had it, that all the IO was issued at once, but I never really questioned why it was slow. And when I did, this is what I found. So we were able to, with cleanups, that big change, and then a bunch of code cleanup and just sort of massaging right around close to 18 gigabytes a second. We will be able to break 20 in the future. How high, sort of hard to say, because we're looking at, and because DirectIO is lockless, it's a really big improvement in shared file contention if you're able to use it. You'll also improve sort of the contention and performance behavior a lot within an individual client. But of course, that requires using DirectIO, which means that you have to have your memory aligned. And if you ever want to do small IO, man, it's either going to be badly, it's going to perform badly or whatever, you know. And it's just, it's not perfect. Nothing is, but we could potentially do better. And so, thinking about buffered IO, maybe we can do an uncached variant of buffered IO and put together a hybrid of buffered and direct IO, buffered at smaller sizes, new uncached sort of semi-direct IO at larger sizes. That's it. So thank you very much. You can see the LUs mentioned here. There's a few others that are linked, find some prototypes to the existing code. Everything we talked about, except for the buffered IO part, is slated to be in 2.15. Most of it's already in there. And I just wanted to say a quick thank you to the LAD organizers for putting on the conference. I do miss being in Paris, but oh well, it's not so bad here. And a thank you to Nathan Ruttman, Shilong Wang, and Andreas Stilger for various bits of assistance in getting this work moving.